So again, what we're focusing on today is solely just solving. A lot of the times you just have to make sure you're paying attention to what the directions are explicitly asking for, how many solutions you're asked for, and where that kind of tells you where they're located. So most of the time it'll say solve the following. It'll say something to the effect of find all solutions on 0 to 2 pi. Now, most of the time, the 0 is included, the 2 pi is not, because you're thinking of it, obviously 0 and 2 pi are the same location. So normally if the solution is there, you would include the 0 and then not include the 2 pi. So a lot of the times, this is how your notation, how the question will be asked. So again, just thinking about the warm-up, our main goal is always to isolate that variable, to get that x by itself. Your solving doesn't change. Like, that whole process doesn't change. We're just trying to get x by itself. So we have 2 sine of x equals -1. Then we divide both sides by 2. So the sine of x would equal -1/2. Now, this is why I kind of mentioned might be a little bit helpful. You know, obviously you always want to be pushing yourself to be thinking about this without the unit circle, because when you are in calculus, you will not have that available to you. But at this point, as you're still practicing and getting used to it, again, sine is our second coordinate. Where is that sine -1/2? So it would be at 7 pi over 6. And 11 pi over 6, where sine would be -1/2. So if these were your directions, find all solutions from 0 to 2 pi, you would just list it as 7 pi over 6 and 11 pi over 6. Now, if you were asked for all solutions, this is what that would look like. You would have that 7 pi over 6, but again, if you think about your unit circle, you would also have another solution, a full rotation later, and a full rotation later, or a negative rotation back the other way. That would also be a same solution. So it would be, you will see often it written in this way, where you add 2 pi n, meaning you're adding n represents the number of rotations around the unit circle. So that's another way, say on an ACT, that you might see these solutions listed. Could be then 11 pi over 6 plus 2 pi n as well. So the period of sine is 2 pi. So if it asks find all solutions from 0 to 2 pi, this would be your proper response there. But if it asks for all solutions, you would include all of those coterminal angles. So all of the angles in the same location, just another rotation around, positive or negative. So let's take a look at the next one then. If I have the tangent squared of x, if I add 3 to both sides, then I'd take the square root. So the tangent of x would be equal to, now don't forget you guys, when you take the square root, you have to account for the plus or minus. So don't forget, whenever you take that square root, you have either the positive square root of 3 or the negative square root of 3. So where is tangent square root of 3? I know you guys don't necessarily have this written in on your unit circle, but it is at all of our pi over 3 spots. So those solutions would just be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Again, because they're positive and negative. If it were just the positives, I would be in the first quadrant and the third quadrant. If it were the negatives, I'd be only in the second and fourth quadrant, but it asks for both. Now, if you want to think about all solutions with this one, just another kind of little look at this. thinking about this for a second, if you're at pi over 3, remember the period of tangent is just pi. So pi over 3 and then this 4 pi over 3, which those are two of the solutions, are just 1 pi apart. So I could represent that by saying pi over 3 plus just pi n. So that would take care of this pi over 3. It would also take care of the 4 pi over 3. It would then go back to the pi over 3 location and just keep going around and around and around. And then I could do the same thing at 2 pi over 3. And because the period is just pi, all of the solutions would be accounted for there. Okay. Last one's a little bit different. It's you kind of feel like, oh, maybe I should be like factoring or something, or subtract cosine from both sides. But guys, here's what I really want you to just think about with this one. Where is sine equal to cosine? Where are my sine values simply just equal to my cosine values? When does that happen? What radians does that happen at? Yeah, what do you think? Pi over 4. And then where again? 5 pi over 4. Why not 3 pi over 4? 3 pi over 4 has, one of them is a positive value, one's a negative. Absolutely. So definitely just kind of not necessarily a lot of solving to do on that one. You're just really thinking about where is the sine equal to the cosine. And that is just happening at pi over 4. Skipping 3 pi over 4 because they're not equal. One's positive, one's negative. And down into that 5 pi over 4 as well. So really it could be just that pi over 4 plus pi n, because it would be happening every pi after that. Okay. So like I said, on most assessments, really this is all we'll be looking for. Just kind of wanted to expose you to how you might see that possibly in the future or on any standardized testing. Okay, so that's like level 1. Level 2, we step it up a little bit. Now, I kind of provided a little side-by-side here, just so the factoring didn't seem overwhelming, okay? But we did already kind of look at this a little bit in our warm-ups as well. So as you look at just the algebraic equation, you're always looking to pull out the greatest common factor. In this case, I would pull out an x. I'd have a 2x minus 1 left. Both of those factors I would then set equal to 0. So I would have either x equals 0 or x equals, that would, turn into 1/2 if I set 2x minus 1 equal to 0. So what I want to push you guys on is now the same thing can happen with these trig functions. You can treat it in the same manner. I will pull out a common factor so that solving becomes easier. Now guys, if you have your calculator and you're, kind of on a time crunch, could you just plug it in your calculator and see where the zeros are? Yes. But it also, in this case, might even be faster to just factor here. So I'm pulling out a factor of cosine, just like I pulled out a factor of x. So I would have, the 2 would still be there. That number 2 would still be within the parentheses. I only pulled out one of the factors of cosine, so I'd still have one factor of cosine still there. But with this factor of cosine being pulled out as the greatest common factor, I would just have a minus 1 there. So look at the similarities here. In this one, the x was the greatest common factor. In this one, it was cosine. And now I solve each one of these separately. So when is the cosine of x equal to 0? I'll get to that in just a second. In this case, 2 cosine of x minus 1 equals 0. I would add the 1 and divide by 2. And at this point, you guys, you've done pretty much all the solving you need to do. Now we need to think about, where does this happen? What angle has a cosine of 0? Again, if we were on the interval from 0 to 2 pi. So if we're on the interval 0 to 2 pi, where do these solutions happen? So really I'm just looking at, let's see, where's cosine 0? Cosine is your first coordinate. Cosine is 0 at pi over 2 and 3 pi over 2. And where is cosine positive 1/2? Where is cosine positive 1/2? So that would be at pi over 3 and 5 pi over 3. Positive 1/2 cosine values at pi over 3 and 5 pi over 3. There's really no rule or anything on how you have to like give your final answer. Obviously, most of the time we would go from in increasing order. So I'd kind of list out the final solutions here as pi over 3, pi over 2, 3 pi over 2, and 5 pi over 3. So those are all 4 of my solutions between 0 and 2 pi. So I don't want you to take a couple minutes here. Look at the next one. Solve this guy first to help you along in solving this guy. It is factorable. So just take a minute there, work through those. This one is factorable. So again, as we think about this one, 2x and x would be our only options for the first 2 terms there. Because they're multiplying together to be positive, but then adding together to be negative, both would need to be negative. 3 and 1 are our only options for factors of 3, so I believe it's minus 3 here, minus 1 here. So x is 1/2, x is 3. So again, I hope, you won't always need to do this. I just hope it kind of shows you how then this guy would be factorable. So instead of 2x minus 1, I'd have 2 cosine x minus 1. Instead of x minus 3, you have cosine of x minus 3. And it's still equaling 0. And then our thought here would be, again, for if these 2 factors are going to multiply together to be 0, one of them has to be 0. So that would allow us to find our solutions here. So 2 cosine x minus 1, when does that equal 0? When does the cosine of x minus 3 equal 0? Again, we're only looking on the intervals 0 to 2 pi. So I'd add 1. This should look a little familiar here. We actually just found that in this one above here, whereas the cosine of x equal to 1/2. So that was at pi over 3 and 5 pi over 3. Now, this one hopefully caused you some pause here, because when I add 3 to both sides, we talked about this a little bit last week. When is the cosine 3? This should throw warning flags everywhere because sine or cosine and sine are never bigger than 1. So you can pretty much know that no solutions are coming from that term. There is never an angle where the cosine value would be 3. Cosine's never bigger than 1, never smaller than -1. So that guy there's no solutions there. Your only solutions for this one would be that pi over 3 and the 5 pi over 3. Okay. Any questions so far on the first page before we get into some more difficult ones here? Okay, so go ahead and flip it over. Will you do me a favor and change this to sine, just because we've done cosine quite a bit? So take a moment here, try to solve the first one. Change it to sine for me. This one does say right across the top, solve on the interval 0 to 2 pi. It's just an inequality instead of interval. So take a moment here with this one. So 2 sine x, if I subtract 4 from both sides, that would be 1. Divide by 2, that's 1/2. So where is the sine 1/2? Positive 1/2. So as you look, sine would be positive 1/2 at pi over 6 and 5 pi over 6. Questions there? All right, let's talk about this next one here. So obviously this is secant. It's going to eventually be related to cosine, but let's get it isolated. Let's try and get that secant isolated first. So definitely add 4 to both sides. Divide by 3. And then take the square root for sure. I do want to isolate the trig function all the way. So the secant of x would be equal to plus or minus the square root of 4/3. Now, at this point, you might want to, you don't have to, but the square root of 4 is 2. Square root of 3, obviously irrational, so I'm just going to leave it here. Now, this would mean then the secant is 2 over the square root of 3. That would mean the cosine is the reciprocal of the secant. So the cosine, where is that positive or negative square root of 3 over 2? So because of the fact that it was squared here, that's where this plus or minus comes from. So there aren't just 2 solutions here, there are 4, because there are 2 positive square root of 3 over 2, 2 negative square root of 3 over 2 ratios, and they're all happening at the pi over 6's here. That's where our cosine is square root of 3 over 2. Square root of 3 over 2. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 would be our solutions between 0 and 2 pi. Okay, now this is where it starts to get a little bit interesting, because as you can see on this one, before I had sine equals cosine, it was great. But now I have sine and then cosine squared, which is a little bit different. So guys, this is where this sheet starts to become one of your very best friends here. Because if you remember, we have all the trigonometric identities up here, but we also have the Pythagorean identities here. Now, the one we talked about the most was this guy, that sine squared plus cosine squared is equal to 1. Now, why this is helpful, if you look at something like this, this is helpful because it allows us to almost switch back and forth from sine to cosine as long as it's squared here. So what I mean by that is, let's write that Pythagorean identity down. If I have sine squared x plus cosine squared x equals 1. I want to replace this cosine squared with something so that it matches up with, it's kind of relating sine to sine. Like, I don't want it to be in both trig functions. So if you look at the way that this is set up here, let's get the cosine squared by itself. To do that, I can subtract the sine squared from both sides. And cosine squared of x is equivalent to 1 minus sine squared x. Again, why this is helpful is because I can replace cosine squared with something that includes just sine. And then my entire equation will be in just one, in terms of one trig function instead of in terms of 2. So 1 plus sine of x, I'm going to keep that right side, or left side the same. I'm going to bring that 2 down, but I'm going to replace cosine squared x with 1 minus sine squared x. Again, the goal in doing this is now it's all in terms of sine, and hopefully I can factor. Hopefully I can, kind of get some things equal to 0, and I'll be able to factor this. So let's start working through this algebraically. So if I distribute, that's 2 minus 2 sine squared x. Now when I factor, I don't typically like my squared term to be negative, so I'm actually going to add the 2 sine squared to both sides. I have sine x just kind of hanging out there still. And then if I subtract 2 from both sides. If I subtract 2, that would be then 1 minus 2 is negative 1. Is it factorable? Is it factorable? Hopefully it is. Let's try. So I would have 2 sine and sine. I know it has to be 1 and 1. Oh, yeah. And then let's think about if it would be positive or negative. So overall, I want it to be positive when I add them together. So I would put the plus 1 here so that this would be plus 2 sine. And then minus the 1 here, so it would be minus sine. If I did that, this would factor out correctly. So set each piece equal to 0. So 2 sine x equals 1, sine of x equals 1/2. Or when does sine of x equal negative 1? And at this point, I just jump to my unit circle. Where is sine 1/2? Actually, I think we had talked about that one above. Sine is 1/2 at pi over 6, 5 pi over 6. Where is sine negative 1? So again, sine is your second coordinate. It is negative 1 down at 3 pi over 2. Okay. All right, the next piece is going to be a little bit tricky, so why don't you guys take a 2-minute break and then stand up, stretch if you need to, and we'll jump back into it. So last piece, guys, I just want to be pretty transparent too. Like, these equations on the front, very fair game. Common, the solving's very common here, on the top and the bottom. These two also very common. I would say this one, obviously there was quite a bit more involved there with using the Pythagorean identity, switching that, moving everything to the left side, and then factoring. So obviously a little bit less common, but good exposure just to kind of see how you could work those in there. But these ones are fairly straightforward too. They just have one extra added level. So as you look at what's happening here, these are called the multiple angles because when you look inside the parentheses of each of these trig functions, instead of just the angle being theta or being x, it's either a 2x in here. Oh, in this case, there happens to be a pi x. And it could also be a fractional, x over 2 or 2 theta here. So what I encourage you to do is think about, obviously I want you to kind of be thinking about these in the same way, but then when it comes down to the end, when I'm normally just able to say, okay, what angle has a sine value of 1/2, we're still going to be thinking in that way. We're still going to be thinking what angle produces XYZ, but we're going to then have to adjust that solution because of the fact that we have a 2x or a pi x or an x over 2 here. So the solutions at the very end then get a little bit adjusted because of that. So the approach doesn't necessarily change. It's just an extra thing to think about when you get to the end. So here's what I mean by that. If I subtract square root of 3 from both sides, again, I'm just solving an equation with my end goal being to isolate the x value. So here's where I first pause and think, okay, so tangent is by itself. X isn't necessarily by itself, though, but I want to be thinking here and are asking myself, what angles do have a tangent value of negative square root of 3 on the interval 0 to 2 pi? So when you think about your unit circle, the square root of 3, this would be positive square root of 3 for your tangent value. So negative square root of 3 would be happening in quadrant 2 and quadrant 4. So that's where those values would be. It's happening at, or would happen at 2 pi over 3. So instead of saying x would be 2 pi over 3, all you need to do and adjust is that 2x would be equivalent to that pi over 3. And then when you think about solving an equation, isolating the x, you would be dividing by 2, or it's almost easier to think about it as multiplying by 1/2 to isolate that x. So in this case, x would be equal to, I'd divide by 2 or multiply by 1/2 to get rid of that 2. So if I think about multiplying by 1/2 over here, it would just be pi over 6. So my solution here would be pi over 6. Now think about what would happen if you plugged it back in to check it, right? If you plug it back in here, pi over 6 times 2 would be pi over 3, and the tangent of pi over 3 is negative square root of 3. That's what we're trying to do. So it's just this extra little step to go from here to here to get the x fully isolated. So then in this case, one more solution would be, so we said, oh shoot, I forgot the 2, you guys. I'm sorry. It was because it's in the second quadrant. Sorry, guys. So it would be 2 pi over 3, where the tangent is negative square root of 3. My fault. So then you would have 2 pi over 6, which would reduce to pi over 3. Sorry about that. Your other solution that would be negative is down in quadrant 4 at 5 pi over 3. So now instead of just x being 5 pi over 3, it's 2x equals 5 pi over 3. And again, I just multiply by 1/2 to get the x by itself. So it would be 5 pi over 6. Okay. So think about the next one. Guess what? There's no even isolating here that's happening. It's literally saying, where is the cosine of pi x equal to 1/2? So asking yourself, where is the cosine 1/2? That's one we've talked about a lot already today. So the cosine is 1/2 at pi over 3 and 5 pi over 3. But instead of saying x is equal to pi over 3 and 5 pi over 3, I say pi x is equal to pi over 3. Pi x is equal to 5 pi over 3. And at this point, to isolate x, you'd be dividing by pi. You might want to think about it as multiplying by 1 over pi. So when x equals 1/3, obviously the same thing would happen over here. So it would be 1/3 and 5/3 as our solutions here. Sorry, it's a bit getting under the cord there. Okay, next one, I'd add 1. So when is sine equal to 1? So sine is equal to 1 just at pi over 2. There's only one solution here. From 0 to 2 pi. So it's just pi over 2. So instead of x equaling pi over 2, it's just x over 2 equals pi over 2, because I would be taking the sine of whatever's in here, sine of pi over 2. So I need to make whatever's in here, x over 2, equivalent to pi over 2. Multiply both sides by 2. So x is just equal to pi. And last but not least, where is cosine, oh, again, 1/2. Why don't we throw a negative 1/2 in there just for funsies? Let's make it negative 1/2 because we've talked about positive 1/2 a lot. So where is cosine negative 1/2? So cosine, first quadrant, negative 1/2, 2 pi over 3, 4 pi over 3. So I want 2 theta to be pi over 3, or 2 theta to be, sorry, we said negative 1/2, so it would be 2 pi over 3 again. And then 4 pi, down here at 4 pi over 3. And again, we'd be multiplying by 1/2 to get the theta by itself. So theta would equal 2 pi over 6, which would be pi over 3, 4 pi over 6, so 2 pi over 3. This cosine is negative 1/2 at 2 pi over 3 and 4 pi over 3 down here at 4 pi over 3. So again, just one extra little step here when you have the x that's being adjusted as well, because we're taking the tangent of whatever is grouped here. So I am asking myself, what is the tangent of angle would this be? And I set whatever's in that parenthesis equal to that angle to then adjust my final answer there. Okay? So your